We shall never cease exploring the unknown in air and space. With a successful launch and powerful takeoff, we've started a historic voyage. NASA's Voyager probe, launched in 1977, marked the start of an interstellar trip, showcasing its potential to monitor not only Earth but also our entire solar system and beyond furthermore. Even after 45 years, these spacecraft continue to supply scientists with new insights into space. Despite having 3 million times less memory than a regular smartphone and 38,000 times slower than a 5G internet connection, the Voyager probes remain at the forefront of space exploration. These two probes astounded the globe with their historic missions to Jupiter, Saturn, Uranus, and Neptune. They are currently continuing their trek through interstellar space. Scientists, including those born after the era of these ships, are using data from Voyager to uncover riddles in and beyond the solar system. But now, in a surprising twist, the Voyager spacecraft has made an incredible finding. What are they doing now? What will the Voyager spacecraft encounter next? Join us in uncovering these mysteries. Grand Tour. Once-in-a-lifetime arrangement. Interplanetary. Two of the most amazing spacecraft ever launched would never have taken flight if the stars hadn't aligned perfectly. In this case, the alignment involved the 4 largest planets in our solar system. Due to this rare coincidence, a spacecraft could gain speed from the gravitational pull of each massive planet it passed, as if being pulled along by an invisible rope. This alignment only occurs once every 176 years, necessitating a mid-1970s launch to capitalize on the opportunity. NASA seized this once-in-a-lifetime chance by creating 2 identical spacecraft, Voyager 1 and Voyager 2. Launched within 15 days of each other in the summer of 1977, these spacecraft embarked on a remarkable journey from Cape Canaveral, Florida, with Voyager 1 propelled by the Titan IIIe Centaur rocket on September 5th, and Voyager 2 following suit on August 20th. The primary mission of these brave explorers was to investigate the gas giants of our solar system, Jupiter and Saturn, along with their moons. However, they far exceeded their initial objectives, journeying to the farthest reaches of our celestial neighborhood. Over nearly 45 years, Voyager 1 and Voyager 2 have set numerous records, outlasting any other spacecraft in history and traveling further from Earth than any human-made objects. Their journeys have taken them into interstellar space, making them the first human-created objects to cross this boundary, which marks the dividing line between the Sun's sphere of influence and the rest of the galaxy. They will likely hold this distinction for many more decades. The data sent back daily by the Voyagers from over 12 billion miles away has been invaluable to scientists, providing groundbreaking insights and surprising physicists with their findings. The Voyagers' longevity and success are particularly remarkable, given that their missions were originally intended to last only 4 years. As pioneering interstellar probes, Voyager 1 and Voyager 2 continue to expand our understanding of the cosmos, demonstrating the enduring power of human ingenuity and the relentless pursuit of knowledge. Overall, their legacy is a testament to the remarkable achievements possible when seizing the rarest of opportunities in the vast expanse of space. Voyager's interstellar journey. 2 of the most amazing spacecraft ever launched, Voyager 1 and Voyager 2, would never have taken flight if the stars hadn't aligned perfectly. This alignment involved the 4 largest planets in our solar system and allowed a spacecraft to gain speed from the gravitational pull of each massive planet it passed, as if being pulled along by an invisible rope. This rare alignment only occurs once every 176 years, necessitating a mid-1970s launch to capitalize on the opportunity. NASA seized this once-in-a-lifetime chance by creating 2 identical spacecraft, Voyager 1 and Voyager 2. Launched within 15 days of each other in the summer of 1977, these spacecraft embarked on a remarkable journey from Cape Canaveral, Florida, with Voyager 1 propelled by the Titan IIIe Centaur rocket on September 5th, and Voyager 2 following suit on August 20th. Their primary mission was to investigate the gas giants of our solar system, Jupiter and Saturn, along with their moons. However, they far exceeded their initial objectives, journeying to the farthest reaches of our celestial neighborhood. Over nearly 45 years, Voyager 1 and Voyager 2 have set numerous records, outlasting any other spacecraft in history and traveling further from Earth than any human-made objects. Their journeys have taken them into interstellar space, making them the first human-created objects to cross this boundary, which marks the dividing line between the Sun's sphere of influence and the rest of the galaxy. They will likely hold this distinction for many more decades. The early observations of Jupiter's and Saturn's moons, which they provided to stunned researchers 40 years ago, revealed the presence of active volcanoes and fissured ice fields on worlds that astronomers had assumed would be as inactive and crater-pocked as our own moon. Voyager 1 arrived at Jupiter in March 1979, 546 days after its launch, while Voyager 2, which had taken a different course, arrived in July of the same year. Their Vidicon cameras, equipped with red, green, and blue filters, captured full-color images while being built to be stable platforms. With a rotation rate more than 15 times slower than the crawl of a clock's hour hand, they barely spun at all as they traveled across space, reducing the likelihood of visual blur. The spacecraft began transmitting the first images of Jupiter despite still being around 3 to 4 months away from the planet. The incredible diversity of moonscapes the Voyagers found near Jupiter and Saturn was not predicted. The first indication that there might be more moon types than astronomers had imagined appeared when the Voyagers were still 1,000,000 miles or so away from Jupiter. One of their devices, the Low-Energy Charged Particle, LECP, detection system, detected some peculiar signals. Io had active volcanoes, as revealed by the cameras on board the Voyagers. The little world, which is slightly bigger than Earth's moon, is now understood to be the solar system's most volcanically active body. The components ejected by the moon's volcanoes are what give Io its hues and the anomalous ions that strike the LECP's detector. Pele, the greatest of Io's volcanoes, has produced plumes 30 times higher than Mount Everest, and its ash field is almost the size of France. The Voyager spacecraft captured more than 33,000 images of Jupiter and its satellites in total. Every photograph seemed to reveal something new. Jupiter had rings, and Europa, one of Jupiter's 53 named moons, had an icy covering that was shattered and now thought to be more than 60 miles thick. The spacecraft received a farewell kick of 35,700 miles per hour as they were leaving the Jupiter system, thanks to a gravity assist. Without it, they would not have been able to escape the sun's gravitational pull and travel to another star. The Voyagers split off at Saturn. Voyager 1 passed by Titan, the moon cloaked in orange smoke, and then turned north away from the plane of the planets after hurtling through Saturn's rings and taking hundreds of strikes from dust particles. Uranus and Neptune were the next stops for Voyager 2 alone. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later, it flew by Neptune. In 1986, Voyager 2 discovered 10 brand new moons orbiting Uranus, bringing the planet's ringed world count to an ever-growing number. 3 years later, Voyager 2 observed the fastest wind speeds ever recorded for a planet in the solar system, up to 1,000 miles per hour, as it passed around 2,980 miles above Neptune's azure methane atmosphere. Triton, the biggest moon of Neptune, was discovered to be one of the solar system's coldest locations, with a surface temperature of just -391 degrees Fahrenheit, -235 degrees Celsius. Nitrogen gas and powdered particles were ejected 5 miles into the moon's atmosphere by ice volcanoes. If Carl Sagan, an astronomer who was a member of the mission's imaging crew, hadn't been there, Voyager 2's pictures of Neptune and its moons would have been the last ones ever taken by either of the spacecraft. NASA intended to turn off the cameras on both spacecraft once the grand tour was formally over. There would have been no photo opportunities after Neptune, only the unending nothingness and impossibly far-off stars. Despite the fact that the project had been extended in the hopes that the Voyagers would reach interstellar space and had been renamed the Voyager Interstellar Mission, Sagan pleaded with NASA leaders to order Voyager 1 to send one more batch of pictures. As a result, the probe pointed its cameras back toward the inner solar system on Valentine's Day in 1990 and snapped 60 final pictures. Earth was captured in the most mesmerizing of them all, known by Sagan as the pale blue dot. At a distance of 3.8 billion miles, it is still the furthest depiction of our planet ever captured. Earth is hardly discernible in the photograph, hidden by dim sunlight that was reflected off the camera's optics. It doesn't even take up a whole pixel. NASA has implemented a series of measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been turned off to conserve energy, allowing them to operate well into the next decade, with an estimated mission end date of 2030. For the scientists and engineers who have been part of this extraordinary journey from its inception, the culmination of the Voyager missions is a bittersweet moment. Their dedication and hard work have seen the project through far beyond their initial expectations. The data returned by the Voyagers has provided valuable insights, fueled countless scientific discoveries, and inspired generations of researchers and space enthusiasts. As pioneering interstellar probes more than 12 billion miles from Earth, they continue to surprise physicists with their findings. The recent impossible discovery is one of those finds scientists could never predict. We will examine it in greater detail later. The achievements of the Voyager twin probes have been nothing less than spectacular. Their impressive imaging capabilities began to astound scientists and the public even before their encounters with the outer planets. These early images, revealing the gas giant's swirling clouds and iconic Great Red Spot, delighted audiences at NASA's Jet Propulsion Laboratory. However, it was the discovery of active volcanoes on Jupiter's moon Io that truly set the stage for the Voyager's groundbreaking observations. The Voyager missions have not only expanded our understanding of the cosmos, but have also highlighted the power of human ingenuity and the enduring quest for knowledge. Before the recent impossible discovery, the twin Voyagers had already made numerous spectacular findings since their launch. One of the most surprising discoveries was the existence of Jupiter's rings. Although faint, these rings were a revelation and added to the intrigue of the gas giant. Additionally, Voyager 2 revealed that Europa, one of Jupiter's 53 named moons, possessed an icy shell believed to be over 60 miles thick. These findings challenged previous assumptions about the nature of these distant celestial bodies and inspired further investigations into the potential habitability of icy moons. As the Voyagers departed from Jupiter, they received a gravity assist that provided them with a vital boost, propelling them toward Saturn. Without this crucial maneuver, they would not have been able to escape the sun's gravitational pull and venture further into space. Voyager 1 and Voyager 2 soon went their separate ways, each heading towards new frontiers. Voyager 1's path took it close to Saturn's moon Titan, which is cloaked in an orange, hazy atmosphere. This moon's mysteries piqued scientists' interest, leading to further studies of its complex chemistry. Voyager 1 then turned northward, departing from the plane of the planets, and began its journey beyond the realm of our solar system. Voyager 2, on the other hand, embarked on a series of adventures that brought it to the outermost planets of the solar system. In 1986, it made a historic flyby of Uranus, where it discovered 10 previously unknown moons, increasing the planet's moon count. 3 years later, Voyager 2 reached Neptune, revealing the remarkable features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, making it the fastest wind ever recorded on a planet in our solar system. As the spacecraft passed within 2,980 miles of Neptune's azure methane-rich atmosphere, it provided unprecedented insights into this distant world. Triton, Neptune's largest moon, was found to be one of the coldest places in the solar system, with surface temperatures plummeting to -391 degrees Fahrenheit, -235 degrees Celsius. Triton also exhibited unique features, including ice volcanoes that ejected nitrogen gas and icy particles 5 miles into its thin atmosphere. These discoveries expanded our understanding of the variety and complexity of celestial bodies in our solar system, even in the outermost regions. The Voyager's missions have continually pushed the boundaries of human knowledge, offering invaluable insights into the diverse and dynamic nature of our solar system and beyond. The energy that powers Voyager. One individual who played a pivotal role in extending the Voyager missions beyond their initial goals was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing one last set of images before the cameras on both spacecraft were turned off. These images would offer a parting gift to humanity, a final glimpse of our home planet from the distant depths of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back toward the inner solar system and captured a series of 60 images. The most iconic among them, known as the pale blue dot, remains an unforgettable symbol of our place in the cosmos. Taken from a distance of 3.8 billion miles, it is the farthest image of our planet ever recorded. Earth appears as a tiny, pale blue speck, barely distinguishable in the vastness of space. The Voyager mission is an astonishing tale of durability and longevity that reads like a space-age superhero comic. Even after 40 years, these spacecraft are still out there, continuing to send us valuable data from the furthest reaches of our cosmic neighborhood. Now let's talk about their archaic 8-track tape system. Yes, you heard that right. 8-track tapes were all the rage in the 70s, and the Voyager probes still used them. It's a testament to the genius of the mission's designers that these trusty tapes have stood the test of time. But why 8-track tapes, you ask? In those early days of space exploration, digital storage as we know it today was still in its infancy. So they needed a reliable and durable data storage system, and those 8-track tapes fit the bill. They're like the indestructible workhorses of the cosmic age. What's even more incredible is that the data on these tapes isn't just your run-of-the-mill tunes. It's precious scientific data about the outer planets, moons, and interstellar space. These tapes hold the key to understanding some of the most profound mysteries of the universe. As for durability, think about this. The Voyager spacecraft are exposed to extreme temperatures, cosmic radiation, and the vacuum of space, and yet these aging explorers keep on going. It's like sending your grandparents on a trek through Antarctica, and they not only survive, but thrive. One of the key strategies used to ensure the success of the Voyager missions was the use of gravity assist maneuvers, and their role in these legendary interstellar missions was nothing short of brilliant. Imagine two brave spacecraft, Voyager 1 and Voyager 2, setting out on their audacious quest to explore the outer reaches of our solar system. To reach these distant destinations and gather invaluable data, they needed a boost, something more than their own propulsion systems could provide. This is where gravity assists come into play, and it's a bit like cosmic choreography. Instead of relying solely on their engines, these spacecraft performed a celestial dance with some of our solar system's heavyweight planets, using the immense gravitational pull of these giants to slingshot themselves on their way. This clever maneuver allowed them to conserve precious fuel and gain the velocity they needed to visit multiple destinations on their grand tour. Let's start with the basics. Gravity assist, also known as a gravitational slingshot, is all about transferring some of a planet's momentum to the spacecraft as it passes by. Picture Voyager 1 approaching Jupiter, a massive gas giant with a gravitational pull to match, with precision that could only be achieved by the brightest minds at NASA's Jet Propulsion Laboratory. Voyager 1 swung by Jupiter at just the right angle and speed. Jupiter's gravity tugged at the spacecraft, accelerating it to a higher velocity. It's like a cosmic boost, giving Voyager 1 the oomph it needed. But there's an art to this maneuver. The precision required is mind-boggling. Yet, the scientists and engineers behind this cosmic ballet got it right, not just once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. Voyager 2, for instance, used gravity assists from Jupiter and Saturn to take it to Uranus and Neptune. These celestial dances were pivotal in making the Grand Tour possible. The Voyager missions would not have been the same without these slingshots. Voyager 1 went on to reach interstellar space, and Voyager 2 quickly followed suit, all thanks to the precision of these gravity assists. The concept behind gravity assists is simple, but the execution is breathtakingly complex. Voyager 2's Grand Tour required so much precision. Missing any of these slingshots could have meant a failed mission, but the people behind these missions were determined and relentless in their pursuit of knowledge. Although the Voyager missions made use of gravity assist maneuvers to navigate the cosmos, these missions would have been mere celestial daydreams without another critical component: the Deep Space Network, DSN. Think of it as the interstellar telephone line that kept us connected with our intrepid Voyager probes as they journeyed into the great unknown. So, what exactly is the Deep Space Network? It's not as flashy as a spacecraft, but it's just as vital. The DSN is a network of massive radio antennas strategically located in various corners of the world, including California, Spain, and Australia. These gargantuan dishes, ranging from 26 meters to a whopping 70 meters in diameter, are like cosmic megaphones, allowing us to communicate with spacecraft traveling beyond our planet. Now let's talk about its role in the Voyager missions. The Voyager probes, with their cameras, sensors, and instruments, were essentially our eyes and ears in the vastness of space. To make sense of the data they sent back and to give them new instructions, we needed a robust communication system, and that's where the DSN stepped in. Picture this: Voyager 1, on its way to the outer reaches of the solar system, sends a message back to Earth. It's a faint signal, traveling at the speed of light. As it traverses the cosmic expanse, it weakens. By the time it reaches Earth, it's barely a whisper. But the DSN's colossal antennas are poised to catch that whisper. They lock onto Voyager's feeble signal and amplify it, turning it into data that scientists can analyze. The DSN doesn't just receive signals, it also sends commands. Missions like Voyager are dynamic. Scientists and engineers need to tweak their plans, redirect the spacecraft, or adjust their instruments. They send these commands via the DSN, which beams them into space to reach Voyager. It's a two-way conversation between Earth and the farthest human-made objects in the cosmos. One of the remarkable things about the DSN is that it operates 24/7, tirelessly listening for those distant signals. It's like having an unblinking eye on the cosmos, keeping us connected with our spacecraft, even when they're billions of miles away. The Voyager missions are a testament to the power of collaboration and innovation. While the spacecraft embarked on their incredible journeys, the DSN made sure they were never truly alone. It bridged the gap between our planet and the unknown, allowing us to explore the outer planets and venture into interstellar space. In essence, the Deep Space Network isn't just a collection of antennas. It's our lifeline to the cosmos. It ensures that the stories of the Voyager missions continue to be written, even as the spacecraft journey beyond our solar system into the uncharted territory of interstellar space. So, what is the heliopause, and what fascinating discovery did Voyager 2 find there? As the Voyager probes were on their interstellar journey, one of the key milestones they had to navigate was the heliopause. It's the boundary that separates our sun's influence from the vast interstellar space beyond. The exact location of this boundary was a bit of a mystery, with various estimates and theories. Early estimations placed it as close as Jupiter, but subsequent calculations refined our understanding. In 1993, projections by astronomer Bill Gurney placed the heliopause between 116 and 177 astronomical units, AU. To put this into perspective, 1 AU is roughly 93 million miles, the distance between the Earth and the Sun. Gurney's projections turned out to be remarkably accurate, as Voyager 1 reached the heliopause about 20 years later and detected the expected rise in plasma density. Voyager 1 observed an increase in plasma density, but no significant shift in the ambient magnetic field direction. This was unexpected because if the spacecraft had traveled from a region where the magnetic field originated from the Sun to one where it came from other stars, a noticeable change should have occurred. Voyager 2 added to the mystery when it reached the heliopause at the same distance as its twin, 120 AU from Earth, but also failed to detect any magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere was expected to fluctuate in sync with the Sun's 11-year cycle, but this did not align with the data gathered by the Voyagers. The solar wind, which ebbs and flows with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause. The predicted position of the heliopause should have been further out than 120 AU, adding another layer of complexity. Nevertheless, the Voyager data have provided valuable insights for refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of our galaxy. This transition was likely triggered by nearby supernovae, ancient stars that exploded at the end of their lives and heated the surrounding area while removing electrons from adjacent atoms. The boundary between these regions can be likened to a seaside, with turbulent waves and mixed magnetic fields, although the degree of turbulence can vary. The Voyager's observations have revealed small-scale changes near the heliopause, but negligible variations on larger scales. The ageless explorers, Voyager 1 and Voyager 2, continue their solitary journeys through interstellar space, leaving behind the planets and moons they once called home. But what lies ahead for these indefatigable travelers? It's a cosmic guessing game, but here are some possibilities to ponder. These probes are now headed in different directions, with Voyager 1 racing toward the constellation Ophiuchus, while Voyager 2 is making its way toward the constellation Cetus. Although it may sound like they're headed for a cosmic death in 2030 as predicted by some scientists, it is still possible that they'll likely outlast our species, enduring for millions of years. One day, they might encounter other star systems, bringing with them a message from a long-lost Earth. Picture an alien civilization stumbling upon these ancient artifacts of human ingenuity, carrying the golden record, a time capsule of our existence. Who knows what mysteries they might uncover? The heliosphere. Shouldn't a change have been apparent if Voyager had traveled from a region where the magnetic field originated from the Sun to one influenced by other stars? This was a shocker. In November 2018, Voyager 2 reached the interstellar seashore but did not detect any magnetic field changes upon reaching the heliopause at 120 AU from Earth, the same distance reached by its twin 6 years earlier. This added another riddle to the mystery. All theoretical models predicted that the heliosphere should ebb and flow in sync with the Sun's 11-year cycle, yet this did not align with any of them. The solar wind was at its strongest when Voyager 2 arrived, and if predictions were accurate, the heliopause should have been further out than 120 AU. Theoretical models of the interaction between the heliosphere and interstellar environments are becoming more intricate now that the Voyagers are providing actual field data. According to the general image, our Sun left a hot ionized zone and entered a patchy, partially ionized section of the galaxy. This hot zone likely developed due to a nearby supernova. Ancient stars exploded at the end of their lives, heating the surrounding area and stripping electrons from adjacent atoms. The boundary can be visualized as a seaside, with turbulent waves and mixed water. Magnetic fields twist and turn in this tumultuous area, unlike the smooth fields typically depicted by theorists. Voyager's data reveal numerous small-scale changes near the heliopause, but negligible field variations on vast scales due to the heliosphere's influence on the interstellar medium. It is anticipated that the spacecraft will eventually leave these turbulent regions behind and encounter the pure interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be simple, as they have significantly expanded our understanding of the cosmos. The timeless explorers, Voyager 1 and Voyager 2, continue their solitary journeys through the vast expanse of interstellar space, having long left behind the planets and moons they once called home. But what lies ahead for these tireless travelers? It's a cosmic guessing game filled with intriguing possibilities. Voyager 1 is speeding toward the constellation Ophiuchus, while Voyager 2 is headed toward the constellation Cetus. Despite predictions that they might cease operations by 2030, it's possible these spacecraft will outlast our species, enduring for millions of years. One day, they might encounter other star systems, carrying with them a message from a long-lost Earth. Imagine an alien civilization discovering these ancient artifacts of human ingenuity, each containing the golden record, a time capsule of our existence. Thanks for watching. Please like, comment, and share to support the channel. Don't forget to subscribe so you don't miss upcoming interesting videos.